All right, so starting with number 2, state whether or not the function satisfies the hypothesis of the mean value theorem on the given interval, and if it does, find each value of c in the interval a to b that satisfies the equation. So 2, we have f of x is equal to x to the 2/3 on 0 to 1. So just a refresher on the mean value theorem. The derivative of f at c is equal to f of b minus f of a over b minus a. So first of all, what is the derivative of this? 2/3 x to the negative 1/3, and we're evaluating it at the point c. So 2/3 c to the negative 1/3 is equal to f of b, so that would be 1 to the negative, or 1 to the 2/3 is going to be 1, minus f of a, which is make x 0, that's 0, over b minus a, so 1 minus 0. So we end up with 2/3 c to the negative 1/3 is equal to 1. We can multiply by the reciprocal. So we have c is equal to, or c to the negative 1/3 is equal to 3/2. And then following the procedure of how to get c by itself, we can move it to the bottom and take the cube root of it. So 1 over the cube root of c is equal to 3/2. If I want to undo the cube root, I cube both sides. So I get 1 over c is equal to 27 over 8. Since I want c on top, I can just flip both fractions over, which gives you c is equal to 8 over 27. So it satisfies the mean value theorem, and that's our c value. The other thing to note about the mean value theorem is that it has to be continuous at every point of the closed interval, okay? Meaning it can't have one of those points where it like stops and changes, where you have like a corner, a cusp, a gap, okay, things like that that we talked about previously. So if I have something like number 4, which is f of x is equal to the absolute value of x minus 1 on x is equal, or sorry, on the interval of 0 to 4. What do we know to be true about this function? Huh? What kind of a function is that? What are these called? So that's an absolute value function. Okay, shifted to the right 1. Okay, so the graph would be something like this.
Oh, yeah.
Okay.
Right. It would be. That's exactly.
So is that continuous?
No.
No, because it has a corner. So mean value theorem does not apply because there is a corner at x is equal to 1. But then something like 6, we have f of x is equal to ln of x minus 1 on the interval 2 to 4. So first of all, what is the derivative of the ln of x minus 1? What's the derivative?
1 over x minus 1.
Okay, 1 over x minus 1. If there was a number in front of the x or x was raised to a power, obviously we'd multiply by whatever that derivative is for the chain rule. But it's just 1 over x. We want it in terms of c. So it's 1 over c minus 1 is equal to, okay, f of b, which is 4, so the ln of 4 minus 1, the ln of 3, minus the f of a, which is going to be at 2, so the ln of 2 minus 1, so the ln of 1, all over a minus, or b minus a, which is 4 minus 2. So we would need to solve this out on the calculator. So 1 over c minus 1 is equal to, assuming I did this correctly previously, it should be 0.549. So we need to multiply by c minus 1. So then 1 is equal to 0.549 c minus 0.549. So add the 0.549 over, you get 1.549 is equal to 0.549 c. Divide 1.549 over 0.549, and that's equal to 2.8. Alright, so then let's look at a word problem that's all of that particular type. Temperature change. It took 20 seconds for the temperature to rise from 0 degrees Fahrenheit to 212 degrees Fahrenheit when a thermometer was taken from a freezer and placed in boiling water. Explain why at some moment in the interval the mercury was rising at exactly 10.6 degrees Fahrenheit per second. So we're told that the temperature goes from 0 to 212 degrees in 20 seconds. And we're trying to prove that at some moment it was rising at exactly 10.6 degrees Fahrenheit per second. Okay, so this 10.6 degrees Fahrenheit per second is actually our derivative evaluated at C. Okay, so this is actually our f prime of C. because it's like a rate, degrees Fahrenheit per second. Okay, so just kind of a picture really quick of what's happening. Okay, we've got 0 degrees here, 212 degrees, and we've got 20 seconds out here. So we know that we're going from 0 to 212 in 20 seconds, okay? It could be a steady incline that's happening, but more than likely it's doing something more like this, okay, where it's more curved in the sense that it's gonna, you know, initially start slowly rising and then all of a sudden it's gonna rise really, really fast. So we have obviously f prime of c is equal to f of b minus f of a all over b minus a. Okay, so then we should have that f of b is 212, so when we plug the time in, it's 212 degrees minus, at the initial time it was 0, divided by b minus a is going to be the difference is 20 seconds that occurs, is equal to 10.6 degrees Fahrenheit per second. So x is our time, so 0 to 20 seconds. So at 20 seconds, it's 212. At no seconds, it's at 0 degrees. And the total time, b minus a, would be 20 minus 0, or just 20. So then, because we know that the mean value theorem is an existence theorem, since we can say this, then by the mean value theorem, at some point, it had to be exactly, or I guess I should say, had to be rising by exactly 10.6 degrees Fahrenheit per second.
Where are we supposed to put the roses when we separate them? Because you said something about 11:30 and it's almost 11:30.
You have to take them to the teachers. Oh, there's a K5 kid that leaves early. So I need to run the K5 ones over there really quick.
Okay, so we just take them to their classrooms?
Yeah. Give them to the teacher and explain to them what was explained to the middle school and high school teachers this morning.
Okay.
Hold on, let me see something really quick. I don't know if Miss Moore's in her office. She's probably not. I don't know if this one kid gets any that leaves early. 3:26. Miss Moore? Miss Moore? And here's the kids eating lunch. I would run the K5 classes. I don't know which class the kid's in.
Okay.
I would just run the K5 ones over really quick because they're getting ready to start lunch. They should be in their classrooms. So I would start with K5. E3 and E4 is already done. And then if not, then they can catch the kid before they actually leave at 11:30.
Okay.
So if it is, the kid wasn't here yesterday apparently. So I don't know if they're here today or not.
Okay.
But yeah, start with those, and then once lunch is over at like 11:35, you can take up the other ones to the other teachers and collect their envelopes from this morning.
So all the roses that when we're done with elementary should just be our classes and extra?
Yes. Okay.
Do we need to take this to Miss Hughes?
Is that the total list of everybody that's
Yeah.
missing and the grades and stuff?
Mm-hmm.
Yeah, you can, because I'll need the rosters back. Because I need to look at them in a little bit. Okay. Next thing. Use analytic methods to find the local extrema, the intervals on which the function is increasing, and the intervals on which it is decreasing. So, example of that is 16, g of x is equal to x squared minus x minus 12. So first of all, we're going to take the derivative. So what would the derivative of that be?
Two x minus 1.
2x minus 1. If we set that equal to 0 to figure out if we're going to have a min or a max, then we can solve it. X is equal to 1/2. So then if we take the second derivative of it, what do we get of this? 2x minus 1.
Is 2.
Just 2. Huh?
Oh, I was just saying.
Hold on one second. I don't remember. There's one thing I don't remember if we talked about it, so let me see if I can find it really quick. See if it's up here. Wait, hold on. We're not given an interval, are we? I don't think so. Okay. Just trying to find the thing that explains what this means. Trying to see where we talked about it last time, where they had the mins and the maxes to show what we were looking for. Okay, basically, we have that. One second. There we go. Back to the thing. We basically know that we're either going to have a min or a max here at 1/2. And so we're going to use that, and then we'll determine if it's a min or a max in a second. We take this value, okay, just leave this here. This is more for the second part. I just went ahead and did it, okay. We're going to, how does that even happen? Hello? There. Okay. So we're going to take this value and we're going to plug it in for g of x to figure out what the y value is, so we can figure out the actual point that we have our min or our max at. So we have 1/2 squared minus 1/2 minus 12 This is going to be 1/4 minus, I need to get a common denominator to get a 4 on the bottom. We have 2/4 minus 4 on the bottom is going to make that 48. So that's going to be equal to negative 49/4. So the point is 49/4, or negative 49/4. Oh, and the x value is 1/2. So then now this is where this stuff comes in. So if you look at if the derivative is greater than 0 at the point, it's increasing. If it's less than 0, it's decreasing. So, huh? So we would do 2x minus 1 is less than 0. So 2x is less than 1. X is less than 1/2. So, yeah. So this is helping us find where it's increasing and decreasing. So B wants increasing, so it's increasing after this. So it's increasing from 1/2 to infinity, and it's decreasing from negative infinity to 1/2. Since it's decreasing and then increasing, then that shows us that it's a minimum at 1/2 and negative 49/4. There's something about the second derivative as well, which is what I was trying to find, so I didn't make sure, so I made sure I said it correctly. That was something about the second derivative. If it's such and such, then that means it's a min or a max. Let me see where that is. Technically, hold on, this is technically showing C. Let me show B. 2x minus 1 is greater than 0, which means that 2x is greater, x is greater than 1/2, which is what shows that it is, hey, can you tell him that his balloon will just be here when he gets back?
Yeah.
Thanks. X is greater than 1/2, and so that's why it's increasing on B. I kind of just implied that, but I should have actually shown it, so there's that. Really trying to find where it actually talks about the second derivative thing. I may have to find that and come back to that at a different time, because there is something about the derivative, but I can't remember if it's in relation to 0 or 1, which would make a difference. I'll look and get back to you on that about the second derivative thing. All right. The next step says to find all possible functions of f with the given derivative. So this is the stuff for antiderivatives. Okay. So with something like 30, it tells us that the derivative of f at x is equal to 2. So what we do is we're trying to figure out what the original function was in regards to that. So if,
2x.
okay, yeah, so we're doing the opposite. it would be 2x, okay, because there's no variable there already. So you take it, and there's no variable. This was a constant term, meaning that it would have to be something to the first power. So the antiderivative of it is 2x. Now, the important thing is it says all possible functions. That means that we need to add c, because we don't know what the constant that may have been there before, if there was one, okay? Our constant, it could have been like 3, so it could have initially been 2x plus 3. Could have been 2x minus a million. Okay, we don't know what constant value was there, so the c is accounting for our all possible functions. By doing that. No, just plus c, and then c can be either plus or minus. We always say plus c, but c can be a negative or a positive, or it could be 0. So we don't know what it is. In some cases, problems will ask you to actually solve for c. That doesn't come in this section, but it comes, later. So I want to do another example that's not in your book of this, just something similar, and then we'll do a couple more of these with other stuff, because antiderivatives are going to be coming up for a while now, so just to discuss these and stuff. If you had something like f prime of x is equal to x squared, okay? In order to get an x squared, what would my function before that had to have been? Like if I told you this is your function, take the derivative, and you got x squared, what would you have taken the derivative of to get x squared? Like what power would the x have had? Okay, so that would have been an x cubed. Okay. Okay, it would have been thrown out to the front. So when we took the derivative, that would have given us 3x squared. The 3 is clearly not there. So what is some way that I would have canceled the 3 possibly? If what was in front? Okay, if it was divided by 3. So if the original was 1/3 x cubed, then we would have had 3 over 3x squared when we took the derivative, which would have gone away and would have just left us with x squared. Okay, so that's what I'm saying. Like, these aren't really hard. It's just like it's kind of like a mind game, like a brain game or something like that. You gotta like figure out what's missing. Like I've got to find all the missing pieces, and then obviously we would add the plus c, because we still don't know if there could have been a constant term that's not there now that we don't know about. Okay. All right, another one of these, f prime of x is equal to, we just have 2 of these left, just so you know, sine of x. So, what function has a derivative of sine of x? Okay, yep, negative cosine, because the derivative of cosine is negative sine. So, if the sine is positive, then cosine had to be negative, okay? And we say then plus c to account for any constant terms that could have been there. Another one, if we had the derivative of 1 over x minus 1, okay, we're assuming x is greater than 1. What derivative would have given you that? The ln of everything inside of there, right? So the ln of x minus 1 plus c. Okay, now the reason that it specified that x had to be greater than 1 is you can't have the derivative of, so you can't have a log of anything less than 0. Okay, so it's got to be greater than 1. Technically, you can't even have 0, well, because you didn't, you can't have 0, so. Anyways. All right, so problems that I would recommend you look at from this section, 1, 3, 11, 15, 19, 29, 31, and 33. And I'll see if I can find that thing about the second derivative that we were looking at up here, because there is a way that you can use the second derivative to figure out this is a min or a max. I'm just blanking on what it is that you compare it to at this moment.